Hello and welcome. In this video, we'll be diving into the fascinating world of geometric sequences and series. By the end of this lesson, you will be able to define a geometric sequence, find its general term, calculate the sum of its terms, and apply these concepts to solve real-world problems like compound interest and population growth. Let's get started. First, let's define what a geometric sequence is. You might also hear it called a geometric progression. A sequence is geometric if each term can be obtained from the previous one by multiplying by the same non-zero constant. This constant multiplier is called the common ratio, and we denote it with the letter r. So to get from one term to the next, you always multiply by the same number, r. Let's look at an example. Consider the sequence 2, 10, 50, 250, and so on. To check if it's geometric, we divide each term by its preceding term. This should give us the common ratio. First, 10 divided by 2 is 5. Next, 50 divided by 10 is also 5. And 250 divided by 50 is 5. Since the ratio is constant, this is a geometric sequence. In this case, the common ratio r is 5. The algebraic definition formalizes this idea. A sequence u_n is geometric if the ratio of any term to its previous term is a constant, r. That is, u_n plus 1 divided by u_n equals r for all positive integers n. The common ratio, r, can be positive or negative. For example, the sequence 2 minus 10, 50, minus 250 has a common ratio of -5. Notice how the terms alternate in sign. So to recap, a geometric sequence is defined by a constant multiplier, the common ratio, r, between consecutive terms. Now that we know what a geometric sequence is, let's find a formula for its general term, or nth term. This formula will allow us to find any term in the sequence, without having to list them all out. Let's suppose the first term of our sequence is u_1, and the common ratio is r. Let's build the sequence term by term. The first term is simply u_1. To get the second term, u_2, we multiply the first term by the common ratio, r. So u_2 equals u_1 times r. For the third term, u_3, we multiply the second term by r. That's u_1 times r, which simplifies to u_1 times r squared. Following this pattern, the fourth term, u_4, would be u_1 times r cubed. Do you see the pattern emerging? The power of r is always 1 less than the term number. For the nth term, u_n, the power of r will be n minus 1. This gives us the general term formula. u_n equals u_1 times r to the power of n minus 1. This formula is a cornerstone of geometric sequences. It allows us to find any term in the sequence if we know the first term and the common ratio. Let's work through an example to see how to use this formula. Our goal is to find the general term and a specific term of a given geometric sequence. Consider the sequence 8, 4, 2, 1, and so on. First, we need to show that it's geometric. We do this by finding the common ratio. The first term, u_1, is 8. The common ratio, r, is the second term divided by the first, which is 4 divided by 8, or 1/2. We can check this with the next pair. 2 divided by 4 is also 1/2. So the sequence is geometric, with u_1 equals 8, and r equals 1/2. Now, let's find the general term, u_n. We use our formula, u_n equals u_1 times r to the power of n minus 1. Substituting our values, we get u_n equals 8 times 1/2 to the power of n minus 1. We can simplify this expression using exponent rules. We can write 8 as 2 cubed and 1/2 as 2 to the power of -1. This gives us 2 cubed times 2 to the power of -1 times n minus 1. Distributing the -1, we get 2 cubed times 2 to the power of -n plus 1. When multiplying powers with the same base, we add the exponents. So The simplified general term is u underscore n equals 2 to the power of 4 minus n. Finally, let's find the 12th term, u underscore 12. Using our simplified formula, u underscore 12 equals 2 to the power of 4 minus 12, which is 2 to the power of negative 8. This is 1 over 2 to the power of 8, which is 1 over 256. So the 12th term is 1/256. As you can see, the general term formula is a powerful tool for analyzing geometric sequences. Sometimes, you'll be given terms that are not the first term, and you'll need to find the general term. Let's tackle a problem like that. Suppose we have a geometric sequence where the second term, u underscore 2, is minus 6, and the fifth term, u underscore 5, is 162. Our goal is to find the general term, u underscore n. We'll start by writing these terms using our general formula. The second term, u underscore 2, is u underscore 1 times r to the power of 2 minus 1, which is u underscore 1 times r. We know this equals minus 6. The fifth term, u underscore 5, is u underscore 1 times r to the power of 5 minus 1, which is u underscore 1 times r to the fourth. We know this equals 162. Now we have a system of two equations with two unknowns, u underscore 1 and r. A clever way to solve this for geometric sequences is to divide the equations. Let's divide equation 2 by equation 1. On the left side, u underscore 1r to the fourth divided by u underscore 1r simplifies to r cubed. On the right side, 162 divided by minus 6 is minus 27. So r cubed equals minus 27. To find r, we take the cube root of minus 27, which is minus 3. So our common ratio is minus 3. Now that we have r, we can find u underscore 1 by substituting it back into one of our original equations. Let's use the first one. U underscore 1 times r equals minus 6. Substituting r equals minus 3, we get u underscore 1 times minus 3 equals minus 6. Dividing by minus 3, we find that u underscore 1 equals 2. We have our first term and our common ratio. We can now write the general term. The general term is u underscore n equals u underscore 1 times r to the power of n minus 1. Substituting our values, we get u underscore n equals 2 times minus 3 to the power of n minus 1. This is the general term for the sequence. Let's look at another type of problem. What if we're given 3 consecutive terms of a geometric sequence, and one of them is an unknown variable? Suppose k minus 1, 2k, and 21 minus k are consecutive terms of a geometric sequence. We need to find the value of k. The key here is the definition of a geometric sequence. The common ratio, r, is constant. This means the ratio of the second term to the first must be equal to the ratio of the third term to the second. So, we can set up an equation. 2k divided by k minus 1 equals 21 minus k divided by 2k. Now we just need to solve this equation for k. We can cross multiply. 2k times 2k is 4k squared. This equals 21 minus k times k minus 1. Let's expand the right side. Using the FOIL method, we get 21k minus 21 minus k squared plus k. Combining like terms, this is negative k squared plus 22k minus 21. Now, let's rearrange the equation to form a standard quadratic equation. Adding k squared to both sides gives 5k squared. Subtracting 22k gives 5k squared minus 22k. And adding 21 gives 5k squared minus 22k plus 21 equals 0. We can solve this quadratic equation by factoring. This factors into 5k minus 7 times k minus 3 equals 0. This gives us two possible solutions for k equals 7/5 or k equals 3. It's always a good idea to check our answers. If k equals 3, the terms are 2, 6, 18, which is a geometric sequence with r equals 3. If k equals 7/5, the terms are 2/5, 14/5, 98/5, which is a geometric sequence with r equals 7. Both solutions are valid. Let's move on to a common application of geometric sequences, compound interest. This is how banks calculate interest on savings and loans. Compound interest involves repeated multiplication by a constant factor, making it a perfect fit for geometric sequences. Let's consider a simple example. Suppose you invest $1,000 at a 10% annual interest rate, compounded annually. The initial investment, U_1, is $1,000. The interest rate is 10% per annum, which means each year. After 1 year, your money increases by 10%. This means you have 100% of your original money plus 10% interest for a total of 110%. To find 110% of a number, we multiply by 1.1. This is our growth multiplier, or common ratio, R. Let's see how the investment grows. After 1 year, the amount is $1,000 times 1.1, which is $1,100. After 2 years, we take the new amount, $1,100, and multiply by 1.1 again, giving $1,210. Notice this is the same as $1,000 times 1.1 squared. After 3 years, we multiply by 1.1 again, getting $1,331, which is $1,000 times 1.1 cubed. This pattern gives us the compound interest formula. The amount after n compounding periods, U_n plus 1, is the initial investment, U_1, times the growth multiplier, R, to the power of n. The growth multiplier R is calculated as 1 plus the interest rate as a decimal. Let's apply this to a problem. Suppose $5,000 is invested for 4 years at 7% per annum compound interest, compounded annually. What will it amount to? Here, the initial investment U_1 is $5,000. The interest rate is 7%, so the growth multiplier R is 1 plus 0.07, which is 1.07. The number of compounding periods, n, is 4 years. Using the formula, the amount after 4 years is $5,000 times 1.07 to the power of 4. Calculating this gives approximately $6,553.98. So, the investment will amount to $6,553.98. What if the interest is compounded more frequently than once a year? This is a common scenario in finance. Let's consider an investment of $1,000 at 12% per annum, compounded quarterly. This means the interest is calculated and added to the principal 4 times a year. First, we need to find the interest rate per compounding period. Since the annual rate is 12% and it's compounded quarterly, we divide the annual rate by 4. The quarterly interest rate is 12% divided by 4, which is 3%. As a decimal, this is 0.03. This gives us our growth multiplier for each quarter. The growth multiplier, R, is 1 plus 0.03, which is 1.03. Now, let's say we want to find the amount after 2 years. How many compounding periods are there? Since there are 4 quarters in a year, over 2 years there will be 2 times 4, or 8 compounding periods, so n equals 8. Now we can use our formula. The amount after 8 quarters is the initial investment of $1,000 times our growth multiplier of 1.03 to the power of 8. This calculates to approximately $1,266.77. Notice that if we had compounded annually, the amount would be $1,000 times 1.12 squared, which is $1,254.40. Compounding more frequently results in more interest being earned. Sometimes, you might know the final amount you want and need to figure out how much to invest initially. This is called finding the present value. Let's say you need 10,000 euros in 4 years for a holiday, and you can invest at 8% per annum, compounded twice annually. How much should you invest now? First, let's identify what we know. The final amount, U_n plus 1, is 10,000 euros. The initial investment, U_1, is what we need to find. The interest rate is 8% per annum, compounded twice annually. So the interest rate per period is 8% divided by 2, which is 4%, or 0.04. This gives us a growth multiplier, R, of 1.04. The investment is for 4 years, compounded twice annually. So the total number of compounding periods, n, is 4 times 2, which is 8. Now we use our formula and solve for U_1. Our formula is U_n plus 1 equals U_1 times R to the power of n, Plugging in our values, we get 10,000 equals u underscore 1 times 1.04 to the power of 8. To find u underscore 1, we divide 10,000 by 1.04 to the power of 8. This calculation gives us approximately 7,306 euros and 90 cents. So you should invest 7,306 euros and 90 cents now to reach your goal. So far, we've been talking about sequences, which are lists of numbers. Now, let's introduce the concept of a series. A geometric series is simply the sum of the terms of a geometric sequence. For example, if we have the geometric sequence 1, 2, 4, 8, and so on, the corresponding geometric series would be 1 plus 2 plus 4 plus 8, and so on. When we add the first n terms of a sequence, we call this the nth partial sum, and we denote it with s underscore n. There's a clever formula to calculate this sum without adding every term individually. The sum of the first n terms, s underscore n, is given by u underscore 1 times r to the power of n minus 1, all divided by r minus 1. This formula is valid for any common ratio r that is not equal to 1. Let's see how this formula is derived. It's a beautiful piece of algebra. Let s underscore n be the sum of the first n terms. If we multiply s underscore n by the common ratio r, we get r s underscore n. Notice that the terms in r s underscore n are almost the same as s underscore n, just shift it over. If we subtract s underscore n from r s underscore n, all the middle terms cancel out, leaving us with just u underscore 1, r to the n minus u underscore 1. Factoring out s underscore n and u underscore 1, we get s underscore n times r minus 1 equals u underscore 1 times r to the n minus 1. Dividing by r minus 1 gives us our formula. This formula is incredibly useful for quickly finding the sum of many terms. Let's apply the finite geometric series formula to a problem. Our goal is to find the sum of the first 12 terms of a given series. Find the sum of the series 2 plus 6 plus 18 plus 54, and so on, to 12 terms. First, we need to identify the key components of our formula: the first term, u underscore 1, the common ratio, r, and the number of terms, n. From the series, we can see that the first term, u underscore 1, is 2. The common ratio, r, is the second term divided by the first, which is 6 divided by 2, or 3. The problem states we need the sum to 12 terms, so n is 12. Now we can substitute these values into our formula. The formula is s underscore n equals u underscore 1 times r to the n minus 1 over r minus 1. Substituting our values, we get s underscore 12 equals 2 times 3 to the power of 12 minus 1, all divided by 3 minus 1. Let's simplify this expression step by step. The denominator, 3 minus 1, is 2. The 2 in the numerator and the 2 in the denominator cancel out. So we are left with 3 to the power of 12 minus 1. Calculating 3 to the power of 12 gives 531, 441. Subtracting 1, we get 531, 440. So the sum of the first 12 terms is 531, 440. Imagine trying to add those 12 terms manually. The formula makes it incredibly efficient. Now let's explore a more complex and fascinating concept: the sum of an infinite geometric series. What happens if we try to add an infinite number of terms in a geometric sequence? Let's look at our finite sum formula again. S underscore n equals u underscore 1 times 1 minus r to the n over 1 minus r. We're interested in what happens to this formula as n, the number of terms, gets very, very large. The behavior depends entirely on the common ratio, r. If the absolute value of r is greater than 1, the term r to the n will grow infinitely large as n increases. This means the sum s underscore n will also become infinitely large. We call this a divergent series. However, if the absolute value of r is less than 1, something amazing happens. The term r to the n will get closer and closer to 0, as n increases. For example, if r is 1/2, then 1/2 squared is 1/4, 1/2 cubed is 1/8, and so on. The terms get smaller and smaller. If r to the n approaches 0, our formula simplifies beautifully. The term r to the n disappears, and we are left with the formula for the sum to infinity, s. S equals u underscore 1 divided by 1 minus r. This is the sum that the series converges to. This means we can add an infinite number of terms and get a finite answer as long as the common ratio is between -1 and 1. This is a truly counterintuitive and powerful result. Let's see how to use the sum to infinity formula. The classic application is converting a recurring decimal into a fraction. Our goal is to write the recurring decimal 0.7 as a rational number, which is a fraction. First, we can express this decimal as an infinite series. 0.7 is 0.7 plus 0.07 plus 0.007, and so on. We can write this as the sum of fractions, 7/10 plus 7/100 plus 7/1000, and so on. This is an infinite geometric series. Let's find its first term and common ratio. The first term, u underscore 1, is 7/10. The common ratio, r, is the second term divided by the first, which is 7/100, divided by 7/10. This simplifies to 1/10. Since the absolute value of r, which is 1/10, is less than 1, the series converges, and we can use our sum to infinity formula. The formula is s equals u underscore 1 divided by 1 minus r. Substituting our values, we get s equals 7/10 divided by 1 minus 1/10. Now, let's simplify the expression. The denominator, 1 minus 1/10, is 9/10. So we have 7/10 divided by 9/10. When dividing fractions, we multiply by the reciprocal. The tens cancel out, leaving us with 7/9. Therefore, the recurring decimal 0.7 is equal to the fraction 7/9. This method provides a rigorous way to convert any recurring decimal into a fraction. Let's look at another classic problem involving an infinite geometric series, the bouncing ball problem. A ball is dropped from a height of 490 centimeters. It rebounds to 75% of its previous height. We want to find the total distance the ball travels until it comes to rest. Let's break down the total distance into parts. The total distance is the initial drop plus the distance of the first rebound, up and down, plus the distance of the second rebound, and so on. The initial drop is 490 centimeters. Now let's consider the rebounds. The first rebound goes up to 75% of 490 centimeters, and then it falls back down the same distance. So the total distance for the first rebound is 2 times 75% of 490. This is 2 times 0.75 times 490, which equals 735 centimeters. The second rebound goes up to 75% of the first rebound height, and then falls back down. So its total distance is 2 times 75% of the first rebound height. This is 2 times 0.75 times 0.75 times 490, which is 2 times 0.75 squared times 490, or 551.25 centimeters. The total distance is the sum of all these parts. Total distance equals 490 plus 735 plus 551.25, and so on. Notice that the rebound distances form an infinite geometric series. Let's find its sum. For the rebound series, the first term, u underscore 1, is 735. The common ratio, r, is 0.75. Since there's less than 1, we can find the sum to infinity. The sum of the rebounds is 735 divided by 1 minus 0.75, which is 735 divided by 0.25, or 2,940 centimeters. Finally, we add the initial drop to this sum. The total distance is 490 plus 2,940, which is 3,430 centimeters. So the ball travels a total of 3,430 centimeters, or 34.3 meters, before it comes to rest. Let's recap what we've learned today. We started by defining a geometric sequence as a sequence with a constant common ratio, r. We derived the general term formula, u underscore n equals u underscore 1 times r to the power of n minus 1, which allows us to find any term in the sequence. We then moved on to geometric series, which are the sums of these sequences. We learned the formula for the sum of a finite series, s underscore n, and the conditions for a series to converge to a finite sum to infinity, s, which is u underscore 1 divided by 1 minus r. Finally, we saw how these concepts are applied in real-world scenarios, such as calculating compound interest and modeling population growth and decay. You are now equipped with the fundamental tools to analyze and solve problems involving geometric sequences and series. To solidify your understanding, here are some practice questions. Here are 5 practice questions for you to work on. Pause the video and give them a try. Question 1. Find the 10th term of the geometric sequence 3, 12, 48, and so on. Question 2. A geometric sequence has u underscore 3 equals 18 and u underscore 6 equals 486. Find the general term, u underscore n. Question 3. Find the sum of the first 8 terms of the series 100 plus 50 plus 25, and so on. Question 4. An investment of $2,000 is made at 6% per annum, compounded monthly. What will it be worth after 5 years? Question 5. Find the sum to infinity of the series 12 minus 4 plus 4 thirds minus 4 ninths, and so on. Welcome back. Let's go through the answers. For question 1, u underscore 1 is 3 and r is 4. The 10th term is 3 times 4 to the 9th, which is 786, 432. For question 2, we divide u underscore 6 by u underscore 3 to find r cubed, which is 27, so r is 3. Substituting back, u underscore 1 is 2. The general term is u underscore n equals 2 times 3 to the power of n minus 1. For question 3, u underscore 1 is 100, r is 1/2, and n is 8. Using the finite sum formula, we get 100 times 1 minus 1/2 to the 8th divided by 1 minus 1/2, which simplifies to 199.21875. For question 4, the monthly rate is 0.06 divided by 12, which is 0.005. The number of periods is 5 times 12, or 60. The amount is 2,000 times 1.005 to the 60th, which is approximately $2,697.70. For question 5, u underscore 1 is 12 and r is minus 1/3. Since it's less than 1, we can find the sum to infinity. It's 12 divided by 1 minus 1/3, which is 12 divided by 4 thirds, or 9. I hope this video has helped you understand geometric sequences and series. Keep practicing, and you'll master these concepts in no time. Thank you for watching.